Okay, Gibbs free energy is the topic today. This is a measurement of how we can predict if a reaction is going to be spontaneous or not. We've talked about the three areas of concern that allows us to make this prediction. Josiah Gibbs is the first one to put all this together. Again, it is entropy, it is enthalpy or heat, and it is temperature. And he found that if you had an exothermic reaction, which means the enthalpy was negative, delta H was negative, if you had a high temperature, that it will most likely be a spontaneous reaction. And if the delta S, which is the entropy, was increasing or positive, that also meant it's going to be a spontaneous reaction. And he put all this together to give us this equation right here. Delta G equals delta H minus T delta S, or more appropriately, as I put there, in defined standard terms, 25 degrees Celsius most of the time, 1 atmosphere pressure and 1 mole per liter if you're dealing with aqueous solutions. That he came up with this free energy. He called it free energy. In fact, he used F instead of G, but later on scientists put the G there in honor of him. If the delta G is negative, it's considered to be spontaneous. Excuse me. The word for that is exergonic. If it's positive, it is non-spontaneous, and the word for that is endergonic. And so we're going to look at examples of problems involving how to use that equation or just using the delta G. So let's open up our books to pages A9 through A15, as well as problem on page A33. We'll be referring back and forth. This can be a bit tedious, especially this problem right here, because in this particular problem here, we are using we're using delta H and delta S and the temperature of 25 degrees Celsius, standard temperature, which has, of course, been changed to 298 K. But let's take a look at problem number 37. And they give us this equation right here. They want us to find the delta H values in that back area, the appendix, and delta S, and then from that use those values and the temperature, get delta G standard. Okay, if this is the equation, we're going to do just like what we did with the entropy in the previous lesson. That is by taking the products minus reactants. It's going to get delta. It's always products minus reactants. So we take the sum of the delta H values, and that gives us negative 393.5 for the carbon dioxide, and we double it, multiply by 4 the water. Now, when you use that chart, I don't like the way it's laid out. It's one of the weaknesses of the textbook that you use. The central atom, when you draw the Lewis dot structure, is C, so it's going to be found under group 4A listings. Water, the central atom is oxygen, it's group 6A. You think hydrogen would be where to look at it? No, the central atom is oxygen, so you have to go to group 6A, 4A for this, and 6A for this. So we have to keep fumbling around trying to find it. The delta H is the first column on the left, the delta S is the last column on the right. And so you get all these values, the CH3OH liquid. Now be careful, because there's a liquid and a gas, and that happens a lot. And make sure it's O2 and not O. That happens a lot. So you got to make sure you get exactly the right ones. I would not be surprised if you just make at least 3 silly mistakes on the first time you do this assignment. It's right for the picking. Anyway, you should end up with a negative 1453 kilojoules. I round these off to the nearest whole number rather than do the 3 sig figs on that. Delta S, same thing. Oh, by the way, the 0 here, now let me explain the 0 for oxygen. The delta H and the delta G values in the table there that you're using is for synthesis or synthesis reactions, okay? How much energy was used to create that? Since oxygen is already in the atmosphere in pure natural form, there is no synthesis of oxygen, so that's always going to be zero. So any element by itself will have a zero value for delta G and delta H in those scenarios. Entropy is a different story. Everything's got its own entropy, so you have to look those up. At any rate, the delta S standard, you should get a negative 162 joules per Kelvin mole or mole Kelvin, however you want to look at it. And the delta G equation is delta H, which is in kilojoules per mole, minus T, which is 298 Kelvin, as I said, times delta S. The problem with delta S, if you take a look at the label at the top of the column, it's joules per Kelvin mole or joules per Kelvin they'll put in there. Don't forget the mole. They should have a mole in there, but they don't. Regardless, you have to change that to kilojoules because delta G in the column in the middle there, if you see the delta G's right there, you'll see that all those are written in kilojoules or kilojoules per mole. So you have to change that by moving the decimal point over 3 places. So we put that in red right here so you can pick that up. And the K cancels out to leave you kilojoules per mole, and you get 1,405 kilojoules per mole for number 37. Number 41, I did one of the two. This is just using the delta G column and not using the delta H and delta S. So this is just a very simple carbon dioxide, which is a group 4, water, which is a group 6, minus methane, which is a group 4, plus 2 times oxygen, which is 0. Those are the numbers you plug in, and you should end up with negative 581 kilojoules per mole. Again, rounding off to the nearest whole number. All right, and the last one is a pretty simple one. They give you the delta G value. They want you to give the interpretation of what it means in terms of spontaneity. So delta G here is negative, it's exergonic, that means it's going to be spontaneous, so you write down spontaneous. It's I believe that's supposed to be a positive 211, I'm pretty sure it is. Positive 211 kilojoules, that is non-spontaneous, almost anytime it's positive. I say that because of part D. Part G is 7.5 kilojoules. Now there is a range in which you can kind of consider an equilibrium where you're going to have lots of products and reactants both. And that ranges from negative 10 kilojoules to positive 10 kilojoules. So at that point we consider that equilibrium, which means you have significant amounts of products and reactants. All right, so pretty basic arithmetic for problems. Your practice problems. Well, I didn't write that down. Oh, there it is, yep. Oh, now I lost it. I love this smart board. Did I ever tell you how much I really enjoy this smart board? It's just a blast. Anyway, 38, 42 through 46 even. Have fun.